Hi, I'm Dane Quinn from the University of Akron. Today I will do an example dealing with polar motion. Here we have a disk of radius ρ, constant, that is pinned at its center, here at point O, and rotates with constant angular speed, theta dot equals omega. So if theta is this angle between a point P and, say, the horizontal direction, then this angle is increasing at a constant rate. I'd like to find the velocity and acceleration of this point P that is at the edge of the disk, as well as the speed of that point. So we'll start off and identify the position of P as the vector from O to P, and we'll define that as R of P with respect to O. Here the point P is moving along a circular path, so it makes sense to use polar coordinates. But we'll be interested in the velocity and acceleration with respect to the ground, so let's start by identifying directions I and J that are fixed in the ground, so horizontal and vertical. And then we'll identify polar directions, ER and E theta, where ER is the direction from O to P, and E theta is perpendicular. So really, ER and E theta are fixed in the disk. As the disk spins, these directions move with it. And the angle between ER and the horizontal direction I is identical to the angle theta given in the problem statement. So we know how this angle is changing with respect to time. We can relate I and J, which again are directions fixed in the ground, to ER and E theta, directions fixed in the disk. So in terms of I and J, we find that ER is cosine of theta in the I direction plus sine of theta in the J direction, while E theta is minus sine of theta in the I direction plus cosine of theta in the J direction. There's a previous video lecture that discusses changing directions like we've done here. So you could perhaps pause this and go watch that for a minute and come back. And we can also relate I and J to ER and E theta. So in particular, I is cosine of theta in the ER direction minus sine of theta in the E theta direction, while J is sine of theta in the ER direction plus cosine of theta in the E theta direction. So now we've written I and J in terms of ER and E theta, and ER, E theta in terms of I and J. It's the angle theta that relates these two frames of reference. And notice that for this problem, the angle theta increases at a constant rate. So I can actually take this equation and integrate to solve for theta as a function of time. So here, theta dot, and I'll use tau as a dummy variable, theta dot is equal to omega. So again, integrating this with respect to tau from 0 to t, we find that theta of t is equal to omega times time. Here I've assumed that the initial angle is equal to 0, and the left-hand side is just the integral of a derivative, so we end up with theta of t. This angle increases linearly in time, so at any given time, I could take this expression and use that to relate, say, I and J to ER and E theta, or ER and E theta back to I and J. So now, let's use polar coordinates to describe the position, velocity, and acceleration of the point P. And I'm going to start off with a general description of polar coordinates, right? So in terms of R and these directions, polar coordinates describes the position as R in the ER direction. Again, ER is the direction of this vector. So as a result, the velocity of point P is r dot, in the ER direction plus r theta dot in the E theta direction, while the acceleration is r double dot minus r theta dot squared in the ER direction plus r theta double dot and 2 r dot theta dot, all in the E theta direction. Again, these are the general expressions for polar coordinates. So once we decide that we're going to measure the length of the vector and the inclination with the angle theta, then this is the velocity and that's the acceleration. What we need to do now is restrict this to the problem at hand. And again, here's the problem. We have the I and the j, we have the ER, E theta directions. So for this system, the radius, the distance of this vector, is constant. Right, so r is equal to rho. And again, rho was the radius of the disk, and that's assumed to be constant. So r dot here is equal to 0. And likewise, r double dot is equal to 0. So these are a consequence of the constant radius of the disk. Now looking at the angle, theta dot was equal to omega, and that was given in the problem statement. So theta double dot is equal to 0. And again, this arises because the angular speed is constant. So now with these, I can return them back into the expressions for velocity and acceleration, which were written here in general to find the velocity and acceleration of p for this problem. So we find that the velocity of p is equal to, well, r dot was equal to 0, r is rho, theta dot is omega, so we simply have rho omega in the E theta direction. And likewise, the acceleration of p is only this term here, minus rho omega squared ER. Everything else vanishes. R double dot is 0, theta double dot is 0, r dot is 0. So in terms of my polar directions, ER and E theta, here we have the velocity and acceleration of point P. So now I can go and calculate the speed. Well, remember that the speed is the magnitude of the velocity. So examining the velocity, E theta is a unit vector, so it has length 1. And the magnitude of this vector is simply rho omega. So that is the speed of the point P. And notice that it actually doesn't depend on where the particle is. Right? There's no dependence on theta. The speed here is constant. So as the point moves around, the speed remains the same. However, the velocity does change because after all, E theta, which is the direction that's perpendicular to the position, is constantly changing as this point moves around. So here, the velocity changes, but the magnitude of the velocity is constant. Now, finally, I can go back and express the velocity and acceleration in terms of I and j, or directions fixed in the ground. And so, really, all I need to do is take these expressions and write ER and E theta in terms of I and j, which we have done on the previous slide. Here was ER, here was E theta, and we've also gone ahead and determined theta of t. So now, in terms of I and j, the velocity of p is rho omega times minus sine omega t, right, because that was theta, in the I direction, plus cosine omega t in the j direction. And the acceleration is minus rho omega squared in the ER direction, which was cosine omega t in the I direction, plus sine omega t in the j direction. So now we have two different expressions for velocity and acceleration. It's the same vector. In both cases, the velocity of p is a single vector, but we've chosen to represent that in two different ways. So if I kind of go and look at the geometry of the motion, right, I might have the position vector here. So we'll say this is O, so that this is r of p with respect to O. And then the velocity is perpendicular to that, right? So the velocity might be in that direction. V of p. Finally, the acceleration is back in the minus ER direction. So writing the acceleration in red and drawing that from the end of the velocity, we see that the velocity changes in this direction. And that would be the acceleration of p. So again, we can kind of express geometrically the position, and then the velocity, and then the acceleration of the point P in this way. So that's a simple example using polar coordinates, but it should be a good example to get started with, to become familiar with looking at directions that do in fact change in time. Thank you very much, and I will talk to you again with more examples.